All right, well,
Thank you.
thanks everybody for being here, and I thank the Star Party organizers for inviting me down to talk to everybody. It's been a few years since I've been to the Winter Star Party, but of course it's a wonderful place, and I brought some of the cold air. Anybody here from like the upper Midwest or the Canadian? Oh yeah, thank you very much for bringing the cold air, but it's nice, man. This is a great experience. So I'm a follow-on to Charlie's talk. I'm going to bring you guys the chaos with this talk. This is a little technical in a sense, but there's only one equation that you guys are going to have to remember. That's it, just one. I'm going to just blow over some of the other ones just because they're there to kind of throw a little reasoning into my craziness on what I'm going to talk about. But I'm going to give you guys a really good idea of how to go about figuring out how long you should expose if you have a camera. Who are imagers in here? Who still uses a CCD? We got one. And I'm going to say, who uses CMOS? Yeah, a new technology, CMOS. This trick, it's not really a trick, but this technique works with both cameras. I'm just going to say that up front. But a lot of people go places like here, and they want to figure out, well, how long should I expose for? And I'm telling you, it's different here than it would be if you live in an area that's got some light pollution, like suburbia, like where I live. It's different. And this is going to be a cool way for you to figure that out. So a little bit about CCD and CMOS. You know, what's the technology difference between these systems? Why you want to characterize your system, and that's a fancy term for why you want to know things about your camera. What's the read noise? You know, what's the pixel size? What's the, you know, some of the technical details that you need to know so you can run them through a couple of these numbers. How to go about calculating that exposure time. Do you need to take darks and bias frames, especially if you use one of these brand new high-tech CMOS cameras? Short exposures. Can you get by with shooting stuff really short? I think I've got some interesting things to show you about that. And then some takeaways, what's going to happen in the future. And I know Richard's probably going to talk a little bit about this, but this is kind of some stuff that he gave that him and I talked about a year ago. This is a presentation I did out at the Advanced Imaging Conference in Monterey, San Jose, California. The last time, and unfortunately that conference kind of is no more. I think they shut it down, but all their presentations are still going to be available online, so, and free to everybody. So I implore you, if you know, you really want to get more into things like imaging and stuff, you can find their stuff and take a look at it, because some of the world's best astrophotographers would always speak out there. The Advanced Imaging Conference, AIC, yes. So a little bit about how we typically image. You know, at a basic level, all we're doing is collecting photons, right? So photons come into through our telescope, and our detector detects these, and it changes these things into electrons that are read out digitally by our camera. But the more photons that we can get, the brighter our image is, you know, the more detail we can see. And so that's really the goal. So our camera counts these things, and if we had a really perfect camera, it was 100% efficient, there was no noise. If we took like a 1 hour exposure and say for example, we detected 1,000 electrons, if we split that up into 6 10-minute exposures, we'd still get 1,000 electrons. And if we took 1-minute exposures, but 60 of them, we'd still get 1,000 electrons. But the problem is our cameras really aren't perfect. Photons tend to come in randomly, kind of like raindrops. You're outside and it's raining. You get hit one here in the head, you get hit by a raindrop in your arm. You know, they're random things. And so that electron count that creates, our images is random. Well, it still doesn't really, the bottom line, however, in the end, the quality of our image is really determined by how many of these things we collect. And that leads to the question, well, why don't we just take 1 hour exposures, get the best that we can do? Anybody have an idea of why that's probably not a good idea, to take an hour-long exposure? Star trails, a couple, you're 58 minutes in your exposure and here comes this one cloud. Boom, you're done. We don't have control over really what happens. So we don't do that. What we do is we take shorter exposures, and the idea behind these shorter exposures is we can stack all these things together and get very close to what a long exposure would be like. I mean, like absolutely really, really, really close. So not every photon gets counted by our camera. There's a thing called quantum efficiency of a chip, which is how accurate it is at counting those photons. The higher that number, the better it is. And these new cameras that are out there now, these new CMOS cameras over the last 4 or 5 years, have very, very high quantum efficiency. So that's a good thing for us. And lastly, there's noise. We have things called thermal noise. We have shot noise. There's several types of noise that affect what we get in the end, and it affects the resolution of what we can see. All right, so read noise and shot noise. Shot noise is kind of sky dependent. It's more like, it depends on the darkness of your sky. And here, it's pretty darn decent because it's a dark sky. Where I live, it's not really that decent. Shot noise is really high. If anybody lives in the inner city, where you really can't see many stars, it's really high there. So these things mess us up. And that's kind of how we'll go through a few of these things. And maybe we can change how some of these things affect what we do. So the two main imagers over the years have been CCD technology, and now we're really into the age of CMOS technology. And these chips are a little bit different, and it helps to understand a little bit about them, which will make our job a little easier in trying to understand how we can reduce this inaccuracies in the noise. So CCDs are charge coupled devices. They were developed in the 60s and 70s along with CMOS at that time. The big difference with these chips is when you take a shot and your shutter closes, that data is all read out at one shot, boom, okay, off the side of that chip. We have CMOS chips, and these are complementary metal oxide semiconductors. The difference between these chips is each one of those little pixels has electronics attached to it. These analog to digital converters that take that signal and turn it into an electron. Whereas a CCD, that readout happens off the side of the chip by the internal electronics. On the CMOS chip, it happens over each pixel. And these initially tended to have more noise. Anybody remember the amp glow phenomena? Yeah. So that's largely a thing of the past now, but what CMOS chips allow you to do is read these signals out much faster than a CCD. I remember years ago I had a STL 11000 CCD camera, and it took like 20 to 30 seconds when it closed that shutter to when it popped on my screen. I have the same size chip in a CMOS, and it takes like a second and a half. Boom, boom, there it is. And that's the efficiency of CMOS. The other big efficiency is they take much less power to run. So you can get by, with the power, whatever's powering your system, it's not going to be as much of a drain on it. So that's just a little bit about what these are about. There's a lot more stuff there, but I really don't need to go into all of that. So why do we have this huge move to these CMOS sensors? Well, it's right here. Money. $27.99 billion is going to be invested by 2026. In the CCD sensor market, $1.58 billion. That's a lot of money that's thrown into CMOS, and that we benefited from that though because of these huge advances in how they operate. No more amp glow, back illumination, which I'm going to talk about here in a second, and we have chips that are so sensitive and so low noise now that the graininess that you used to see in CCD imaging is kind of a thing of the past. So a little bit about, you know, the improvements. These chips up here on top that I have listed, these are all back illuminated CMOS chips. So the difference between the two here, in a front illuminated type system, your electronics are right under these little micro lenses that are over the pixels. In this case, it's a color camera because you have you know, three different colors. But the wiring and all the stuff that goes with getting that data out was between here and the light sensitive surface. Well, back in the CCD days, back illuminated CCDs were developed where all that stuff was put underneath that light sensitive area. So there was nothing there to block any of the light, and it made those chips very, very sensitive. They learned how to do that with CMOS sensors. The difference is a back illuminated CCD is going to cost you about $10,000 just for the chip. The CMOS ones, obviously we see now, they're in our cameras that we use for our hobby. They're in your car, they're everywhere, in your phone. You know, your phone, if you have one of these or a Google phone or whatever, these things stack images on the fly when you take stuff, if you try them in night mode. I mean, it's amazing. They're everywhere. So back illumination also helped with, you know, helped them develop better electronics, and it got rid of a lot of things like the amp glow and stuff like that. The other cool thing is now we have 16-bit CMOS chips. Now some of you may use a 14-bit camera still, but the 16-bit ones are out there, and that gives you a lot more dynamic range. So a lot of improvements have happened over the years, and this is kind of a really nice time to get into imaging because of the cost and the high-tech part of these systems. So here's just a little comparison of the current CMOS technology, which this is the chip I have, the IMX455. It's the full frame chip, but it's the same if you have like a ASI 2600 or a QHY 2600 camera, same darn chip, except it's just smaller. Same electronics, same everything. In a comparison to some of the more recent CCD cameras. So the KAF 16200, that was the last real CCD that was developed for astrophotography. And this number here, the quantum efficiency, just look at the difference. These new chips are around 90% QE, especially in the blue-green range, much higher than the CCDs. The read noise is on the order of up to, you know, 5 to 10 times lower. I mean, it's crazy. 1.6 electrons, 1.5 electrons to maybe 6 to 12 electrons with CCDs. The dark current, which is the thermal noise, is very, very low with these. And that's really an important thing to remember too, because it used to be you had to cool CCD chips down minus 20, minus 30, minus 35 to get the noise level down. With the current systems, you never have to go any colder than minus 5 or minus 10. You know, it's just incredible. So there really is no comparison anymore between these CMOS and CCDs. It's pretty incredible. But one thing you do need to do, no matter what kind of camera system you're using, you have to do what's called characterization. You need to find out, what read noise does my system have? Is it linear? How do you confirm that it's operating to the specs that the manufacturer that you bought it from says it is? So it's called characterization, and it's pretty easy to do actually. This is just an example of a bias frame from the camera I have, the new CMOS camera, and you can see there's no amp glow, it's really clean, there's nothing, no hot pixels everywhere. Here's an idea of what a master dark frame looks like, pretty clean. But by characterizing your system, you can figure out things like, well, how linear is my chip? In this case, this is one of the new back illuminated CMOS chips. It's a very linear chip, meaning as the light level goes up, there's nothing funky that happens in the electronics. So you can go from very low light to very bright, And you can do that consistently, time and time again. I check my camera, and then does anybody know in here know Adam Block? Probably heard of him before, right? Yeah. So I'm friends with Adam, and I sent him my data because he was interested in this and the linearity. He ran it through some custom software that he had, and in the end, we found out that the camera was nice and linear. So that was a really cool thing. We're like, yep, these guys have really developed a really nice nice system. It has a little bit of weirdness going on in the low levels, but yeah, it's really good. So I can tell you, you can't go wrong if you just.
Let me stop you. Like less than a second, basically.
Yeah, less than.
I've noticed some.
In the very, very low levels, there's a slight bit of variation, and that is this little thing here. In the very low ADU area.
It's low ADU and time. It's short exposure. I've noticed some idiosyncrasies on this.
But you're never gonna see it in your images.
Many seconds and much longer. So
Yeah. It really doesn't affect anything. So in the end, you get these numbers, and in this case here, I used this camera characterization program as part of PixInsight. Many manufacturers' software out there has this ability to do it. SharpCap. There's an old program out there called MaximDL that would do it. If you automate your stuff with something like CCD Autopilot, it'll also do it. But in the end, you're looking for a couple things. You want to know about read noise, you want to know about dark current, your well depth, and your dynamic range, and the gain of your camera. So you compare these numbers to what the manufacturer says, and this is a way that you can find out exactly if your camera's working the way it's supposed to. But those numbers are also important for this little equation I'm going to talk about, which has to do with figuring out the exposure time. You need to know these numbers. So however you get to them, whether you just go to your manufacturer's website or you do it yourself and figure out what these values are, you have to do it. You have to have some way of coming up with these things. So you guys can decide how to go there, but find this stuff out for yourself. It gives you a little satisfaction to know that your camera's working the way they tell you it's supposed to be working, right? You just paid $1,500, $2,000 for this camera. Well, this is a way you can tell that it's working really good. So what that does for us, it allows us to understand what happens when we change the gain in our camera. Because the read noise changes with the CMOS. You double the read noise when you do things like binning with the CMOS, but the read noise is already very low. But that's a little bit different than the way old CCDs operated, So you become the expert of your own system by going through this. But we can use this data to figure out how how long we should expose for. So that's the next part here. So a little bit about noise. Noise is kind of a bane for us because it kills detail. And there's going to be a few little, this is the chaos part of this. There's going to be a couple little equations in here, but this is what they mean. T is going to mean total imaging time, S is subexposure length, N number of subs. P is going to be the sky flux, how bright the sky is. R for read noise, and then this photon shot noise is going to be SN. So you don't have to remember those, but remember, this was done to a very technical crowd out in California a few years ago, so they wanted to make sure they knew what each one of these little parts of this equation were all about. So we're going to talk about read noise, which is the random inaccuracies in our analog to digital converter, and a little bit about shot noise, which is because these photons don't come in at the same time. They come in random. And here's the chaos part. So these three little equations here, this thing called single frame photon shot noise, which is just the square root of your subexposure length times the sky flux. And single frame total noise, we have to add in our read noise. So it's the read noise squared. You add this in quadrature, it's a read noise squared plus the photon shot noise squared. And then we have this thing called stack total noise, which is just how many subs did I take? Well, that's the end part. Here's my read noise again, plus the total time and the sky flux. You don't have to remember those, but those are, that's kind of the background of why what I'm going to talk about actually does work. So this is what noise looks like. Here's a really noisy image, right? And this is an image, it's got some things, some circles in here which are stars and stuff, and this little thing off to the side which, you know, is kind of a grid thing. But that looks like a pretty grainy thing, right? So where's the detail in that? It's not, it's gone. Well, what happens if we make the image less noisy? Now we start getting a little more detail in there. Things start to show up. Oh, now there's something showing up there. We get a little less noisy, a little less noisy, and so forth. And then we get down to right here, and now we can start seeing, oh look, there's a little tiny star up there. You know, there's other little things starting to show up. And that, I think, yeah, there's the least noisy image. Now I can really see that little star up there. This is an approximation of what is about 5% read noise compared to the total noise in your system. That's what it looks like. And that's what we get these days with these cameras. We get something that looks like that. And that's the level about what you should shoot for when you expose. It's a nice, smooth looking image. And you have detail because the noise is pretty much gone. But that's what noise does to our stuff. That's an example of how that messes up the details. So part of that equation is how do we figure out what this photon shot noise is? Well, there's an app for that. And this app is actually, it's an online calculator. It was developed by this brilliant physicist in the UK called Dr. Robin Glover, and some of you may know of him. I know one person here that follows what he does. He was pretty brilliant, and he came up with this sky background calculator that all you need to do is you need to have some way to measure how bright your sky is. You know, some of you have these meters, SQM meters. Maybe you know the Bortle level. Maybe you know the limiting magnitude of what your sky is. You put that value in up on top. You need the F ratio of your telescope, pixel size of your chip, the quantum efficiency of your chip, and that's, you can get that from the manufacturer. And whether you're using a mono or color camera, your filters, whether it's the options are for like RGB filters, narrowband filters. You need to know the bandwidth of the filters. And you put that in there and it spits out a number at the bottom called the sky electron rate. That is that value of P in that equation. And that sky electron rate is how many electrons are raining down from the sky in that random fashion. A brighter sky, you're going to have more of them coming down. A darker sky, less of them. But you can also calculate that another way. Here's an example of this little subroutine within PixInsight that's called Calculate Sky Limited Exposure Script. You put the same stuff in there. You need to tell it, what's my camera, 16-bit? What's my gain? What's my readout noise of the camera? You take an image and you take a little subframe of that image and it'll calculate this bottom number, which is called background flux, which is that same value of the sky electron rate. And I've compared these two and they give you the same number. There's other programs out there that'll do this for you. SharpCap has one. I used to use CCD Autopilot to automate what I did a lot. It had the same calculation within the program that I could come up with. But for me, the easiest way is this online calculator that was put together by Robin Glover. and it's really easy to use. The nice thing about this is you can plan all your exposures before you come here. You know you're coming here. You can kind of figure out how dark the sky probably is here by looking at online light pollution maps and things like that. And you can figure out your exposure times before you come here. You can figure out, maybe after you leave here, you're going someplace that's even darker than here. Well, you can figure it out before you get there. So you don't have to fiddle around, you know, how long should I expose for when I'm out there under the dark sky, and you don't have to waste any time. Okay, so how do we determine this optimum exposure time? Well, there's a couple of ways to do it. However, all of them require you know these things. Read noise of your camera. You characterize your system, you get the read noise. You go to your online, you know, the manufacturer's website, you can get it there. You need to know the gain of the camera. You need to know the well depth of your system. Again, you can find all these online, and you need to know the sky flux. How bright is my sky?
Does the fixed file normally show you the read noise, right?
Sometimes it will, sometimes it won't. But you can calculate it very easily, or you can, you know, I know you use a ZWO camera, they list it, they have a nice graph of that on their website. You know, and a couple of these different methods I'm going to show, they give you the same or very similar results. So one is not necessarily better than the other. Some require a little more input than others, but the easy method is not that much different. You're not going to get like, oh, this one is telling me it takes take a 5-minute exposure, and this one says take a 10-minute exposure. No, one may say take a 2-minute exposure, the other one may say take a 2-minute and 5-second exposure. You know, they're very, very close and accurate. So here's the, this is the Dr. Glover method, the Sharp Cap method. If you remember everything or anything, remember that little thing there, C times R squared over P. It's a very simple little equation. C is just a multiplication factor, and what C means is how much noise am I willing to have in a single sub-exposure compared to the total noise of my system. The recommended value is 5%. That was the 5% is like that last non-grainy image I showed you when it got less grainy and less grainy, that nice smooth one. That is 5%. I actually made that at the 5% noise level. So that's the recommended number to use is 10, but maybe you're a purist and you want to have even less noise in your images. Well, these are the other fudge factors here that you can multiply in instead. R squared is what? That's just the read noise of your camera, right? Read noise squared, and what's the P? How bright the sky is. And where do you get the P? From the online calculator. Or you can take a test sub and you compute it the other way. It's really that simple. And this allows you to determine the exposure times for any sky condition. So I figured it out before I came down here how long I need to expose for. When I go to the Okotek Star Party out in Oklahoma, it's darker than here. I know how long I need to expose for before I get out there. I don't have to fiddle with it. At home, it's quite a bit different because it's brighter there. And generally speaking, the brighter your sky, the less exposure time you need. And some of these values are really, really short. So here's the way you do it within, if you happen to have PixInsight, say, you want to use their sub-exposure script, you take a shot of the sky. You create a little preview around that. You put in the numbers of, you know, read noise and all the same numbers that you would use in the other methods. And it measures this little area of sky, and it spits out this number called the background flux, which is your sky, is that p-value from SharpCap. It's the same thing. PixInsight, however, will give you a few other things. It'll throw in there this limit 1 and limit 2. What limit 1 is, if you just want to, what's called exposing long enough to overwhelm the read noise of your camera, that's what limit 1 is. Limit 2 is this equation that was put together by Charles Anstey, and the idea here is you want to overwhelm the read noise of your camera with light pollution noise, you know, the brightness from the sky. And limit 2 is what gives you the same value as the sharp cat method, which is what? C times R squared over P. That's all you need to know. Remember that, write that down. However, there is another way you can do it, and there's this really cool calculator out there from the Gibraltar Astronomical Society, and it has you put in some of the same stuff again. Here we go: gain, read noise, dark current, full wall capacity. The stuff that's in the details of your camera that you get by measuring it or going to the manufacturer website. In the end, when you run your stuff through this calculator, it comes up with just about the exact same idea. So these are interesting methods to determine what your sub-exposure time should be, and you know, this is a very simple way of doing it. I've done it multiple ways before. This is by far the easiest here, and you come up with the same answer. So this is what I would recommend you guys use, the C times R squared over P. And you can go, you can Google Dr. Robin Glover. He's got a beautiful video out there that goes really into detail of noise and really into detail of, you know, things like setting the right gain and stuff for your camera, which I'm going to talk about next. But it's really a phenomenal, you know, he's just such a bright individual. When it came to determining this stuff, it was like, when I watched it the first time years ago, I'm like, holy cow, I didn't think of it that way, but you know, that's a cool way of doing it, and it makes perfect sense. And I can get all this stuff done before I go anywhere. What you're gonna find with these new cameras is very, very short exposures, like from home. I'm talking on the order of like 30 to 50 seconds, maybe 60 seconds. That's all you're gonna need. It's really interesting. Yeah, he had a question in the back.
Last November, Robin really humbled me when I was interviewing on him too, trying to reconstitute the star color. He had said something really boneheaded out there with him. He's very responsive.
Oh yeah, oh absolutely, yeah.
This man is well worth the I think it's 14 pounds a year. Well worth it.
So here's a couple examples of the differences between a CCD and a CMOS when it comes to exposure time. This is an example of the latest generation CCD that was made for astronomy, the KAF16200. So we took one of these using an f8 scope, 1x1 binning. The read noise of that camera is 7 electrons. We're going to use a luminance filter, which has this 280 to 300 nanometer bandwidth. We're in a dark sky, you know, relatively like here. I was measuring 21.47 or something last night, so pretty close to this type of sky. The camera has an average quantum efficiency of about 50% versus the 90% with the new CMOS. Has 6 micron pixels. The old saying used to be, well, I got bigger pixels, so I collect more light. My camera's better, it's more efficient. And what we're going to go for is we're going to shoot for a read noise of about 5% compared to the total noise of the system, kind of like that nice smooth image I showed you at the end with those little tiny stars that started to show up. And we're going to use the SharpCat Skyflux calculator, that online calculator, to figure out what the Skyflux is. And we're going to run it through some of those other equations I had before. Don't worry about them, but in the end, this thing called single frame photon shot noise with this system ended up being about 6.5 electrons per pixel. The single frame total noise ended up being 9.57 electrons per pixel. And the read noise, which was added to the shot noise, was about 3 electrons per pixel, because it's relatively high read noise camera. Well, in the end, so the percentage of the read noise which was added to that noise, the photon shot noise, was 32%. Whoa, we're looking for 5%. So how long do I need to expose with that chip to get this 32% down to 5%? in this dark, relatively dark sky like here, well, I need to shoot for 690 seconds. And I can verify that because that's about what I used to shoot when I came here with my CCD, about a 10-minute sub-exposure, right? Well, let's look at the BSI means backside illuminated, my back illuminated CMOS. Well, same system. We're going to use the same scope, the same binning. I'm going to use what's called high gain mode on the camera. I've got a read noise level, instead of 7 electrons, 1.57 electrons, so a lot lower read noise. Same filter. The average QE across the entire luminance bandwidth of the filter is about 70%, but I got tiny little pixels, so they're not going to collect a lot of light, right? And we're going to look for that 5% total noise in our system, and we're going to calculate the sky electron rate the same way. I'm going to go into gain here right after this, yeah. So we're going to take the same 60-second exposure, and I find that by doing that, my background sky flux is this value 0.39 electrons per second, okay? So my total sky flux ends up being this. Here's the same thing. The single frame photon shot noise is that. The total noise is 5 electrons per pixel. The read noise, which is added to that total shot noise, in this case now is only 0.25 electrons per pixel instead of like 3. And what is the percentage of the read noise which was added to the total noise? Well, we're there at 5% right now. 60-second exposure versus 690-second exposure. That's pretty amazing, you know, when you think about it. So, with these new cameras, having to shoot, is there a reason why it would be better for you to shoot for 60 seconds versus 10 minutes?
And less mistakes.
More images.
Well, do you have to guide?
Yeah.
Maybe, maybe not. Most likely, if you have a decent mount, you don't have to guide. You know, a quick 60-second exposure makes your life a lot easier. As Charlie was saying earlier, you know, he's got this new light equipment. He's running off an iPad. You know, he's trying. You know, this is part of the philosophy part of what he was talking about. You know, I mean, it's insanely incredible that it's that short, but it is.
But if you're getting the same overall exposure time, you're going to have 10 times the amount of disk space.
Well, there's always something that comes with new stuff, right? And yeah, however, in the end, what you'll find is you'll get a much better result with many subframes from, you know, you're going to stack maybe 30 or 40 subframes from the CCD. You may stack 30 or 40 from the CMOS. You're going to get a nice looking image, but that 30 or 40 subframes took you a whole heck of a lot less time with the CMOS. You know.
When you're talking your 30 second, 60-second subs, that is, are you speaking from the general experience, vast majority of us experience in urban or suburban?
Absolutely, yeah.
5, 6 environments and still narrowband.
When you narrowband's a little different. This is more like RGB type stuff. But you will find when you do these calculations yourself, you're going to have very, very short exposure times.
No, that's what I find too.
Yeah. So here's just this is just a kind of a table it shows you a comparison between, you know, maybe where most of us live is in this Bortle 5 suburban type environment. You know, some are inner city like Bortle 9. Some are lucky they live in Bortle 1. But here's an example of, say you have an f6 scope, which is the average, you know, maybe you have a refractor, it's at f6. And these are the sky electron rates that you're going to potentially get. Here are the exposure times. So this is with a CCD, here's with the CMOS. 8 seconds versus 90 seconds. And it's just a table to show you, it's just a graphic kind of to show you the the extreme difference between these type of systems nowadays. It's not going to, I'm not saying that there's nothing wrong with a CCD camera, because they take wonderful pictures. You just need to know how to operate them correctly, and you need to know how long your exposure time needs to be with those too. Here's an interesting example, and I can verify this one really good, because this is about what I do when I go out west. This is in a really dark Bortle 1 sky. It's showing with this f6 scope about a 53-second exposure is the minimum you want to do. The minimum you want to do is close to 10 minutes with the CCD. So I shoot typically about, you know, I've got an f8 scope, but it ends up being about 4 minutes out there for my color filtered images, where it used to be about 15 years ago. So yeah, so no more, I'm not going to go into much more detail about this. That's just showing you the difference between the systems. There's this thing out there called total stack noise versus exposure time. And what this is you know, what happens if I expose longer? Maybe it tells me that I need to expose for maybe 5 minutes. But, you know, I don't want all those subframes clogging up my hard drive, so I'm going to shoot for 10 minutes instead. It's got to be better, right? Well, what this graph shows you, this is the higher read noise camera. There is a place where the total stack noise over here compared to your exposure time in seconds, that graph flatlines out. The place where it flatlines out here is about right here. What this tells you is if you shoot longer than 240 seconds with this camera, you're not doing yourself any favors. It's not going to make your image any better at all. You can surely go for 10 minutes, but it's not going to help you. So why would I want to do that? Why would I want to guide for 10 minutes when I can do it for 4 minutes, right? Yes. This graph here is for the CMOS, the newer CMOS systems with lower read noise, you know, maybe 1.6 electrons. This flatlines about right in here. So at 60 seconds, there's no reason for me to go any longer than that in this particular case. So that's showing you another difference between the two types of systems. You gain no noise benefit at all in whatever your particular sky background, you know, your sky brightness is. So once you determine those, say you're at home and it says, man, I should shoot for 50 seconds. Yeah, you round it up to 60, that's fine. But there's no reason for you to go any longer than that. And some of you may be in bright enough skies that it's even less, maybe 30 seconds. And then you definitely don't have to guide, right? So, yeah, pretty incredible. Here's a little comparison I did with, I used to have a QSI 583 and a 683. At home, to get to the 5% noise level under my bright suburban sky, I had to shoot for 344 seconds. At low gain with my new camera, now that's down to 80 seconds. High gain, for 2% noise, I'd have to, maybe I wanted to get less noise, so I'm like, oh, I'm going to go with that better value. I'd have to shoot for 800 seconds at home. I can do that same thing in just over 3 minutes now. So, yeah. So what about darks? Yeah, it looks kind of, yeah, it's a very high contrast screen. It doesn't look anything like this on mine, but it's actually pretty smooth. Here's two examples of two images. One was calibrated with just a master bias. One was calibrated with a master dark. There is absolutely no difference in the noise at all, which was pretty interesting when I did the test to see. Here is, let me see here. Whoop. Here is a stack of 30-second, 180, 30 3-minute exposures, 30 3-minute exposures with master darks or just master bias. There is no difference in the noise level at all in these images. It blew me. I was like, interesting. And I remember this in the days I had a Sony CCD. It was very similar to that. These Sony chips are incredible with what they can do. Whether you use darks or not, you need to test your system. You know, not all cameras are equal. In my case, with my system and this camera, I could go without. I mean, I could use darks or not use darks and probably wouldn't see much of a difference at all. This isn't a general rule. It's always better to, you know, calibrate your stuff the correct way. However, you're short on time, you're at a star party, maybe you're trying to get that image in to win the imaging contest. Give yourself the benefit of the doubt and try it and see if it works. In my case, it works just fine. So binning, a little bit about binning. There is a difference between binning a CCD and a CMOS. When you bin a CCD, you make 4 pixels now into 1 pixel. You boost your signal to noise 4 times. The read noise stays the same. When you bin a CMOS camera, your read noise doubles. Okay. However, the read noise of these cameras is already so low, you're still lower than the read noise of the CCD. You're still in really, really good territory. And you do get a 2 times signal to noise ratio boost when you bin a CMOS. So don't be afraid to bin. Unfortunately, if you have a color camera, you probably can't because of the Bayer matrix. But if you have a mono camera, surely you can do it, and you can bin it to fit maybe your image scale a little bit better. I typically use 2x2 binning a lot because I'm at about 1 arc second per pixel at 2x2 binning. And there's no reason to, 1x1 is great, but why do I want to shoot at 0.6 arc seconds per pixel when the seeing is never going to be there, for that. I can always drizzle maybe in processing my data and end up with a resolution of close to what I would have gotten with 1x1 binning. So something to think about. Gain. Typically, most will tell you that the optimum gain to shoot at is where what's called high conversion gain kicks in. So this is an example of a graph. This is from ZWO because this is the camera I have. Where high conversion gain kicks in is right here, where the read noise at low gain is around 3.5 electrons, and as the gain goes up, it stays about the same. And all of a sudden, it dives down to 1.5, and then kind of flatlines out again. This is pretty much the optimum point. For me, it's gain 100. If you use a QHY camera, it's going to be something different than that. I don't know the exact values that they use, but I think somebody told me it's around gain 25, 26, something like that. Now that is the most efficient place to be, and that makes your exposure time really, really short. The problem with that sometimes can be, what if you have a really, really bright object you're shooting, like Orion, and you want to get the inner core? Well, at gain 100, you're going to have to take like a 5-second exposure. So maybe in that case, you would use maybe lower gain to get those exposures, and then use higher gain to get the real faint stuff, and then mix them together when you process. Yeah. So yeah, ZWO has several gain values which are different than the QHY cameras. As you raise the gain up, however, what happens is your well depth goes down, how many electrons you can fit in there. But however, in my case, what I finally figured out, when I go to binning 2x2, my well depth goes back to like 66,000 electrons. And that's plenty. I mean, it's high, that's actually high well depth.
Jonathan,
Yeah.
can I ask you, when you go down to where you were at a gain level where your full well drops, does that still give you the same number of f-stops? Or
It's a little bit less. You have to look at they have a graph on the website. It's a little bit less.
Or do you get the same, in other words, to fill up one ADU, it takes less electrons.
Yeah, it takes a lot less. You're down, the well depth drops. Yeah, the well depth goes from 50 to 16,000 by popping that gain way up at the same binning level. In the dynamic range, drops.
Zero, even though you don't get that.
Yeah, it drops, but it may be perfectly fine. Depends on what kind of what you're shooting. Yeah. So what if you change the gain? What does it not do? Well, it doesn't change the number of photons that you collect over the course of an imaging night. You know, that's a farce. It doesn't make a difference. And it doesn't change the total noise in your final stacked image either. So as long as you use the recommended exposure time that we were talking about on how to calculate that, it doesn't really change anything. So let's see. So yeah, this is just a recommendation. You know, what if I got a really bright object? Well, use.
Quick question on the 2x2 binning now. Is that software or hardware binning? Because they work a little differently in these cases.
They do. His question is, what happens when you bin 2x2? Is it done by hardware or software? Well, in the case of my camera, it's software. So it reads out the full image and then combines the pixels together and then converts it to a lower resolution image. There are some, I believe there are some hardware options, maybe on some of the science cameras. Maybe QHY has it. They're a little bit different. But most of people in this room probably are using a ZWO camera, and that's going to be a software. If you have a QHY and have that option, you know, you better read pretty carefully about how that works.
On these IMX imagers, at least on my Movarian, not on the Chinese ones, but
Yeah. Okay, so it possibly.
But you have to change the way it operates
Mm-hmm.
On the driver level setting.
Okay. Interesting. Yeah, I don't have a Movarian camera. So what Tim is saying is, if you have a Movarian camera, they offer a hardware option of some sort. And actually, I believe ZWO offers one, but it's not something that most of us would typically use, you know. Okay, so now we have these new cameras that you could take advantage of short exposures. Well, here's an example of taking advantage of this low read noise by taking this was a shot of AGC 4395. I took 2 hours of LRGB and 6 hours of HA, 60-second subs. This was at a dark site now. I wanted, you know, I got together with my buddy Richard Wright and we kind of did a test to see how this would work. 120 60-second subs. I took 460 second subs through a 5 nanometer HA filter. HA, 60-second subs with an f8 telescope, okay? So here's an example of a stack of 179 of those 60-second subs with HA. Here's a stack of my normal 20-minute sub exposures, stack of 9 of them, the same amount of time. This was at home here, at home under a suburban sky. Do you see much of a difference between those? There's hardly any. The only difference is there is a little bit of what's called quantization error in this one. If you really zoom into this thing, some of the faint stuff that you may see there, you don't see as well over here. But I mean, it's at that super low level. 60-second, who wants to take 60-second HA exposures instead of 10, 20 minutes, right? Yeah, it looks like right here. It looks nice on my screen. But anyways, I mean, this was pretty incredible. It works really good. Short exposures. Don't have to guide. Don't have to. Now you got to have a computer. You got to have a hard drive that you can store all those big sub files on, right? You know, each one of mine is 120 megabytes. I don't know what you guys are having when you download, but it takes a lot of storage space. And that's one of the things that just goes with new technology. So the takeaways are. BSI CMOS performance now just blows away older CCDs. It's a fact. I was a naysayer when I first heard about these cameras, but you know, they actually do. They have 3 to 10 times lower read noise. They have higher QE. They still can have excellent well depth, which was a problem with some of the earlier ones, but not these. That higher QE and lower noise gives you an opportunity to have exposures that are much shorter at the same noise level than with the older systems. Most CMOS are small pixels, and they typically are more suited to moderate size instruments, but that's what we have as amateurs, right? We don't have a Hubble in our backyard. We've got moderate size instruments, and it's usually a good pixel scale. There are these cameras called scientific CMOS that are out there. that even have lower read noise, but they're a little pricey still. But in a few years, maybe not. Maybe you need to use darks with yours, maybe not. Try it and see how it works. Measure the noise level in your images, your stacks, by using maybe master biases versus master darks. And see. Mine it works. Try it with yours. Binning in software doesn't increase sensitivity like a CCD, but you do get a doubling of your signal noise ratio. And camera cooling. Please don't cool your CMOS down to -25 and -30. I mean, you can do it. You're wasting power, and you don't need to. It's not going to make your image any better. That's centigrade, but you can run it that cold, but -5 to -10 is really as cold as you need to go. I mean, when you look at the thermal noise properties of your camera, you're going to find that getting that cold is going to make absolutely no difference, because it's just not going to make your image any less noisy. It's pretty amazing. Yeah, very high quantum efficiency with these new cameras, 85 to 90%. Mine averages throughout the whole spectrum, from the bluest blue all the way to S2 is about 70%. But that's still 30–40% higher than just 5 years ago with the CCD. It's pretty incredible. Yep. So that's the bottom line right there. So a little thing about the future. When I was talking to my buddy Richard, I guess is talking tomorrow, coming in this afternoon. Soon enough, we're going to get to read noise levels that are close to zero. And when that happens, you're going to be shooting your DS, your deep sky stuff like guys do planetary now. You're going to turn your system on. It's going to take very short, quick exposures. It's going to auto stack them and auto calibrate them. And you're going to watch that image build up, similar like a sea star. And you're just going to decide, how long do I want it to go for? Maybe 3 or 4 hours. And then you're going to have an image. And yeah, I mean, but we're going to have to get down to close to zero, but it's going to happen, because they're already down to like 0.5, 0.4. It's not too far away. So you won't need to guide anymore. It'll stack and calibrate on the fly. Yeah, you're going to need a 3 petabyte drive to hold it all, but that's just the way it is, But that 3 petabyte drive will be that big. So.
SD cards.
Yeah. We still need to do some work on the there's a little overhead that happens, and then we'll have AI and noise rejection algorithms that'll just auto fix things on the fly. So your little stars in the corner that are elongated because maybe you don't have the best optics in the world, well, you're never going to know. It's going to look perfect. It's going to look fine. Yeah, if you guys look at this later, there's just some nice references here that a lot of this data came from, if you want to see it. Okay, and that's the end of this one. Maybe if you want a couple-minute break, take off. I'm going to talk a little bit about some interesting stuff I do now, which is imaging, called Adventures in Imaging the Unknown. Taking advantage of this really cool technology now and having the correct exposure time, and I'm going to start that in maybe a few minutes, and then I'll run through that, and you're welcome to stay for that if you'd like, and thank you so much. So.
Thank you, guys.